Okay, so we're going to be talking about acids and bases, and we'll just get into the very introductory parts of it today with some basic definitions. Acids and bases very much affect you each and every day. Who had apple juice or orange juice this morning? Really? Oh, good, thank you. So acidic, right? Yeah. So we tend to eat a lot of acids, and who had a salad or leafy greens last night? You had some bases. And who brushed their teeth this morning? Good job. Slightly basic, sodium fluoride. And did you do any baking last night? Cooking?
Oh, yeah.
Yeah? Huh? Paninis. Fabulous. A lot of good grease in there. No? Yes, Tiffany will bake all of us something, and you will tell us whether you used acidic or basic ingredients. In any event, a lot of the foods you eat are acids and bases. Everybody went pee-pee this morning. Urine is slightly acidic. Your blood, slightly basic. In fact, if blood pH drops too low, acidosis can set in. That can be extremely dangerous. We'll get into that a little bit more. Hopefully you cleaned up after yourself last night, and your cleaning agents tend to be a little bit basic. If your garbage disposal stinks, you can put a little bit of vinegar down it. Vinegar is 5% acetic acid. So we'll be linking a lot of this together today. As I said, pretty much basic definitions today, and talking about different types of acids and bases, how they react, what they generate. Then we will be getting into pH determination and interpretation. And finally, we'll be able to name acids and bases. And this will be a continuation of something we did in Chapter 5 but didn't apply much to acids. You already know how to name bases. You just didn't realize they were bases. And then finally, we'll talk about titration, which is a technique used to determine the concentration of an acid or a base. And you'll be doing that experimentally in the lab probably toward the end of next week. So we've got a lot to cover. This is a great chapter because it's going to tie everything together now, things we did back in stoichiometry, solutions in terms of molarity. So this will be a good way to review for this semester exam, and we'll talk more about that in a week or so you know exactly what's going to be on it, what to prepare, etc. Okay, so in terms of some basic definitions for acids and bases, there are 3. We're going to focus on 2. I'll mention the third, but it's not something I'm really going to assess. The first definition is the Arrhenius definition. Back in 1887, a Swedish chemist published a paper talking about acids and bases. And his focus was on which ions get generated when the substance is dissolved in water or mixed with water. And what he found was, regardless of whether you dissolve an acid or a base in water or mix it with water, both acids and bases conduct electricity. So if you have a solution, you hook it up to some type of electrical source or a light bulb, the light bulb will illuminate. But what he did notice was that acids will ionize in water to generate protons or hydronium ions, so H+. Bases will ionize in water to generate hydroxide ions. So for example, if you have the acid hydrochloric acid, it will ionize in water, and you'll see the generation or production of protons. Hence, this substance is an acid. A base, such as sodium hydroxide, will ionize in water to generate sodium ion and hydroxide ion, and the generation of hydroxide ion indicates that you have a base. So acids that are Arrhenius generate protons, bases that are Arrhenius generate hydroxide ions. It's easy to recognize an Arrhenius base because it'll be some type of metallic cation with hydroxide ion. Don't confuse something like CH3OH for a base. That's methanol and alcohol. So Arrhenius bases have metallic cation hydroxide ion. They generate hydroxide ions. Arrhenius acids generate protons. Now this definition is a little bit limiting because the solvent has to be water. So with Arrhenius acids and bases, acids generate protons, bases generate hydroxide ions, and the solvent is water. So this is the Arrhenius definition. We'll come back to Arrhenius acids and bases in a lot more detail when we talk about titration, because what happens there is you react them together, you generate a salt and water, and there's a lot you can determine, the theoretical yield or the actual yield of the salt. You can determine the concentration of one of the substances, and we'll talk more about that next week. A second definition is the Bronsted-Lowry definition, and two scientists working independently, Bronsted and Lowry, independently proposed a new definition because they felt that the solvent wouldn't always be water, so there had to be something else to consider when talking about acids and bases. So they're going to look at what happens during the reaction.
How did they know there was a difference between solvents?
Just in terms of what they mix, so they could, for example, have...
Like how do they determine there was acids and bases?
So if you take hydrochloric acid from a bottle and you mix it with water, you can, there's a lot of different ways to do it, but with a low pH, that suggests that there's a lot of proton in solution, hence you have an acid. If you have a very high pH, greater than 7, that suggests that there's very little proton and more hydroxide ion, hence a base. But they knew what they were mixing together. With the Bronsted-Lowry, for example, they might use a substance such as ammonia and mix it with water, and they could test what the pH was after the reaction. So there's a lot of different ways to do it, but if you didn't use water, let's say you used hydrochloric acid and ammonia, you don't have any water in there, so water wasn't your solvent, so you would look at a different solvent in that case, and that's what Bronsted-Lowry looks at. All right? Yes, yes? Okay. With the Bronsted-Lowry definition, they're going to use different solvents, and they're not going to focus on what gets generated, but rather what happens during the reaction. So during the reaction, what's going on? And what they noticed is that acids donate protons. When they donate protons to a base, the acid forms a conjugate base. I'll go into this in just a minute. A base accepts protons, it forms a conjugate acid, and the base accepted the protons from the acid. So the acid donates the protons to the base accepts the protons from the acid, and we're going to look at what gets generated. But the key thing with an acid that's a Bronsted-Lowry acid is it is a proton donor, a base is a proton acceptor. The acid forms the conjugate base, the base forms the conjugate acid, and this seems very confusing at this point, so let's walk through, give a lot of examples, and you'll feel very comfortable with the definition of a Bronsted-Lowry acid, its conjugate base, a Bronsted-Lowry base, its conjugate acid. Now, if you look in some textbooks, they'll go and react Bronsted-Lowry acids and bases right away, but it was never clear to the kids what formed and why. So we're going to start much simpler. Those of you in the back sitting together, your focus is way off. You're either going to focus or you're going to separate because it's not going to help you to understand. All right, so we've got a list of acids here. We've got a list of bases. An acid is a proton donor. So a Bronsted-Lowry acid is a proton donor. It's going to donate a proton. It donates it to a base. We'll worry about the donation to the base in a few minutes. I want to take a look at what the acid forms when it donates its proton. Now, when it donates its proton, it loses it. So the acid donates its proton and forms a conjugate base. This is what's left over when the acid loses its proton. So the acid is H plus and Cl minus. So when you get rid of the H plus, what you have left is Cl minus. That's its conjugate base. And we'll go over the naming of the acids. I'll use the names now, but you'll understand how to name and you'll be able to name later next week. So this is hydrofluoric acid. For those of you who watched Breaking Bad in season 1, he told him to go out and buy hydrofluoric acid and dump it in the bathtub. I'm sorry, to dump it in the container that was safe. The kid didn't listen, dumped it into the bathtub. And if you watched, you know what happened. I'm only in the middle of season 4, so don't mess me up. Don't tell me what happened.
Wait, would it melt through bone though?
Bone?
That was the one thing they were arguing about, is that it wouldn't, you said it would go through the bone or something?
Who said it wouldn't?
I thought Walter said it was like, something about the bone was like the problem with it, or like...
No, the problem was putting it in the tub. It was a porcelain tub, so hydrofluoric acid eats away at porcelain, but it didn't eat away at the type of plastic that he told him to buy at Home Depot. In regard to the bones,
it would melt through your bone?
hydrofluoric acid's a weak acid. I don't think it would melt through bone. If you have, for example, a clamshell and you treat it with hydrochloric acid, it does dissolve the shell. I'm not sure. We'll take a look at that.
Alright.
Do you know any acids that do melt through bone?
I would imagine some of the strong ones do, but I mean fleshy skin for sure, like sulfuric acid, battery acid, will definitely melt away your flesh. I think I wouldn't use the term melt, but it probably would react with it. Let me write up a reaction. We'll take a look at that. Once you understand acids and bases, we'll look at it in the second half. That's a good question. I like it. Please don't try it at home. All right. Not funny. Hydrofluoric acid then is the acid. So you basically have H plus, F minus, so to speak, although hydrofluoric really is covalent. So you have H bonded to F, but if you think about it in an ionic standpoint, it might be easier to determine the conjugate base. Just be careful because it is covalent. So you're going to generate F minus because you took away an H plus.
Should you take away fluorine?
You take away H plus. So what you have left is F minus for your conjugate base. All right, so H2SO4 is sulfuric acid. That's the acids found in car batteries. We're going to take away one H plus because when the acid ionizes, it donates one proton at a time. Go ahead. Yep.
So we have to put the minus.
Yes, because if you added back a proton, the negative and the positive would make neutral, and you'd have H2SO4. So absolutely no negative, wrong.
So all the conjugate bases are negative?
No. A conjugate base will have a 1 minus charge if the acid was neutral. If the acid was negative, the conjugate base will have a 2 minus charge. If the acid were positive, the conjugate base would be neutral. We have examples of all of those, though. All right. So this is bicarbonate ion.
So we CO3 minus?
Exactly. 2 minus. 2 minus. CO3 2 minus.
Because it's a negative.
Right. This is
H2.
PO4 minus, right? Now what about this? This is dihydrogen phosphate ion. This would be
Two minus.
yeah. Now water's very interesting. Everybody's like, water's neutral. Water has the ability to act as an acid or a base. And we refer to substances that can act as acids or bases as either amphoteric or amphiprotic. Like ambidextrous. Ambi means both. So somebody who's ambidextrous can do things with both hands. I can eat with my left hand, I can eat with my right hand. No, I can. Substances that can either act as acids or bases, that is, be proton donors or proton acceptors, are amphiprotic or amphoteric. And we'll get into that more because you'll see quite a few examples here. Water's one. So water has the ability to either donate or accept. Another example that you'll see here is the bicarbonate ion. The bicarbonate ion has the ability to accept or donate. And another good example is ammonia. Okay, so those are just a few examples. But very often, these polyatomic ions with a negative charge have the ability to do both. So water has the ability to accept a proton, so what would it make?
HO minus.
H,
O minus.
right, and instead of writing ho ho ho, we tend to write OH minus, a hydroxide ion, because water is HOH.
Is it wrong if you do put HO?
It's not wrong, but you'd never see it in a book. And it'll help you a lot if you do OH minus, because down the road when you do more complex acid-base chemistry, it just signifies that you have a base. Okay, so what would NH3 form if it acted as an acid? NH2 minus. Now this one's very interesting. This is acetic acid. Hang on. You'll remember the Ku group back from when we drew the compounds, which feels like 6 months ago.
Was it?
I think it was, maybe more. The ionizable proton here is the one in green. Okay, so you actually make CH3, then what?
COO minus.
You got it.
So why do you always have one on the end?
Because if you draw it out, it's the weakest bond of all. You don't lose H's that are attached to carbons. All right?
Oh, is that one attached to it?
You lose the H that's attached to the O. Do you want me to draw that guy out? So if you have acetic acid, Jillian, can you hit the white light switch with the red tape, please? Thank you. So this is hard to see. Thank you. This is the ionizable proton. You don't clip an H that's attached to a C. With acids, you'll see you typically, you're going to clip an H attached to an O if it's
Why do
ternary.
you take it off from L to the C? Is it just like it's easier to take off?
It's carbon does prefer 4 bonds. That is true. It's probably an issue of stability. I was thinking it might be an issue of probably an issue of bond energy, which we didn't cover this year. This that's what it is. So what you're looking at here is this bond is weakened by the electronegative oxygen here. So it's drawing the electrons toward it. This oxygen here fully also pulls the electrons toward it, weakening this bond. Hence you get cleavage there. It's a complicated issue. We'll hit it in AP. It'll make more sense. I was thinking in terms of bond length as well. And That's actually not going to work, so I'm not going to go there. But that's what it is. This bond is weakened because the electrons are drawn toward the more electronegative atom. Clip it, and it cleaves. All right. In terms of the last one listed there, what would be the conjugate base of the ammonium ion?
NH3.
Yep. All right. So bases are proton donors.
Wait, why is it?
No, I just said that wrong. Bases aren't proton donors. What are proton donors?
Acids.
Acids, of course. Acids are proton donors, and bases we're going to hit next. Jillian, what's your question?
How come if it's positive, it doesn't have a charge?
Because if you have $1 and I take it away, how much money do you have? None. So if you have an initial positive charge and you take away an H plus, you take away one H and the positive and you're neutral. All right. So acids are proton donors. They form conjugate bases. Bases are proton acceptors, and they form conjugate acids. So for example, water can act as a base. It's neutral. It's neutral in terms of its charge. It accepts a proton, and it forms H3O+.
So that would be HCO3.
This one, be careful now, you have to gain a proton. So you have one H, you gain one, so now you're going to have 2. And that's going to be
So
carbonic
it wouldn't be minus
acid.
anymore, though.
Say it again?
So you wouldn't have a minus though.
No, because if you had minus, if you're $1 in the hole and you get $1 back, now you're even.
Okay.
All right,
So you just add an H
now we're going to add an H plus.
So you add the plus.
Right, so if you're neutral, you become positive. If you're negative, you become neutral. So this is neutral, so what is ammonia going to form as its conjugate acid? You got it. Usually the H goes in front unless you have a Cu group. So bromide ion's going to become hydrogen sulfate ion will become oopsie. That didn't come out very nice. Sulfate ion becomes
HSO4 minus.
all right. Give a shot on the rest of them. Take about a minute. Let's go. You can do it. You can do it.
So it becomes a plus.
This one? No.
What if it already had a charge? Does it become like
Neutral.
neutral? So the 2 minus charge become neutral?
No, because you're only getting one H
So it
plus.
would be like just minus?
Correct. I'll type them in. You'll tell me what we need to go over. I can't hear her question. Go ahead.
Would it ever be 2 plus? Like if it's already positive and it gave
No. And that's an excellent question. It was something I was going to go into. Give me a sec. Questions on the posting. You've got this? You're good?
Wait, can you do the one that's really long?
Yeah, all you're doing here is you're adding a proton, and it always adds to the Cu group. So you replace the minus with an H because the positive cancels the minus. Yes? All right. What we're going to do now is we're going to react the acid with the base, but I want to address your question because it's a good question and it links right here beautifully. So sometimes what happens here is if you just have to pick out the acid and the base. The kids usually don't have any difficulty with it or the conjugates, but I'm also going to make you predict the products of a Bronsted-Lowry acid-base reaction. And some of the kids struggle with this because they overdo the acid, and I'll show you what I mean. So for example, H3PO4 is phosphoric acid. Okay? PO4 3- is phosphate ion. The charge on phosphate ion is 3-. Generally speaking, with 2 exceptions I can think of, the most H's you can have hooking up with that ion corresponds with the charge, 3. If you have, say it again?
Does that work for anything?
Well, that's what I'm going to show you. So if you have, for example, carbonic acid, this is a carbonate ion, 2-, the most H's here. So you're not going to get 2+ type situations because that'll mean you're putting more protons on than the anion can accommodate. So, and there's numerous examples of it.
So like a lot of the polyatomic ions that have the minus charge, like you add like, so if it's like 3-, you can add 3 H's.
And the polyatomic, yes, and those polyatomic ions will have oxygen in them. That's another good point with the acids. The only 2 exceptions I can think of are the hydronium ion. Now O is 2-, yet you can generate this, and ammonia. I take that back. Ammonia makes ammonium ion, and N is 3-. So these are the 2 examples I can think of where you do have more hydrogen than the charge predicts, but you see these so readily that I don't think it becomes an issue. And this is a hydronium ion. We'll get into this more next time. Okay? This is the ammonium ion. That's on the back of your periodic table. All right, so that's a good point to make, and that'll help us with our prediction. What we want to do now is we want to react acids with bases and see what they generate. These will be Bronsted-Lowry acids and Bronsted-Lowry bases, so the base will not have OH in them. An acid and a base react to form their conjugate pieces. For example, hydrochloric acid and water. Now, soon you will know that hydrochloric acid is an acid, so you'll recognize it. But if you didn't, if you compare this substance with this substance, you will see they differ by a proton. So this substance lost a proton. It donated it to the water. So the acid forms the conjugate base, and the base forms the conjugate acid. Looking at this set here, let's do some of these together. Now, ammonia and water, we know, are both amphiprotic or amphoteric, so you can't guess right away what's what. So my approach is to look at this substance and look at a substance similar.
So it's base, right?
So this substance, to make this substance, accepted the proton. So as Chloe said, this is a base. A base reacts with an acid, and the base forms the conjugate acid, and the acid forms the conjugate base. Yes? Yes? All right, who wants to help me with the next one? So many volunteers. Helen,
The first one, acid,
how come?
because it had a 50-50 shot.
Okay, 50-50 shot is true, but your approach should be to look at it and look at the substance on the other side that's similar. Did it lose a proton or gain a proton going from left to right?
Lost.
It lost. That's why this is the acid. So it reacts with the base. So what is the acid form?
Conjugate.
They go together. They're complementary like peanut butter and jelly, my least favorite thing in the world. So acid goes with conjugate base.
Everything.
And the base forms the conjugate acid because it's gained the proton. All right, Helen, you got to do another one.
Alright.
Let me just set it up for you. Compare this and this.
It gained one
It gained one. So if it accepts, it's a,
base.
you got it. And the base forms, let's do it this way. There you go. That may be the easier approach for you. A base reacts within.
Turns into acid.
Well, the base reacts with the, reacts with the acid, hydrochloric acid. And what is the acid form?
The conjugate base.
You got it. Is that a little better?
Yeah.
All right. You want to do another one?
No.
All
I
right.
think Brie does though.
Who does? Bree? All right, Bree. Same approach. Compare the left and the right.
It's an acid, a base, and then a
Okay, hang on. My typing's lacking. Acid, base.
conjugate base.
You got it. See, she thought she put you on the spot, but you knew your stuff. Alrighty, I'll make that blue. I'm not sure it's the same blue. The blues are like a mess. Alright, now the next set's a little harder. And this is where that quality question came in a few minutes ago, because now you'll be far better equipped to answer it. I look at these two substances, and I know phosphate ion has a 3- charge, so I've got as many H's there as I can hold. So is it going to accept another one or give one away?
Get one away.
So that makes it the acid. Acids react
Oh, you
with
have
bases.
To, you have to know your prior knowledge of this?
Prior knowledge, I know. What were they thinking? Yes, darling.
Can you repeat that one more time, please?
This piece here?
Yeah, the last
Yes. So I looked at the first substance, and I know that phosphate ion, PO4 3-, has a 3- charge. So it has as many hydrogens as it can accommodate, so it's not able to accept another one. That makes it the acid.
So you know how to have the periodic table?
Hang on. One question at a time. Go ahead.
How do you know it can hold as many hydrogens?
What's the charge on phosphate ion?
3-.
3-. How many hydrogens is it holding, or does it have in its chemical formula? 3. Max out. Okay? And that goes back to Layla's question initially. That's what I was illustrating here. Okay? Go ahead, Q.
Are we gonna have to look at the periodic table to figure out the charge? If it's
You might, but I think at this point a lot of you are so strong with your formula writing. I think you know more than you think you do.
but can we look at it as a
Yes, for those of you going to AP, that's something you'll want to learn this summer. Was there another cue? No, you're not going to memorize the periodic table, silly. But they don't give you the names of the elements, and they don't give you the polyatomics. It's all right here. Oh,
We have to know all of those elements.
oh,
You have like, you'll give us like a list of what we need to know.
oh.
No?
Oh, yes, of course. All right. Now, did you have a question? Okay. The acid forms a conjugate base. What's the conjugate base of this acid?
H2PO4 minus.
You got it. And now you can see the importance of the exercise we did initially, because the kids used to really struggle with this. Ions are aqueous. Aqueous. Oh, it's not coming out right. Aqueous. There we go. I'm not writing AQ. All right, and what is the base form? 3. Right? Yes, yes? Yes, yes. Brave soul for the last one. Do do do. Really? Seth, go ahead.
Okay.
Shh.
Well, the first one's a base,
Okay.
and the second one's an acid.
Okay.
Yeah.
There's more than one answer on this one, so we'll work it both ways for those of you who are like, oh, he's not right. He's right. All right. What are we going to form?
You are going to form H2SO3.
Yep.
And NH2 minus.
Yep. Good job. So that's one possibility. This is acting as a base. It accepts the proton from the acid. It forms the conjugate acid. This is sulfurous acid. And the conjugate base. Now, some of you may have come up with a different answer because there is more than one possible answer here. And maybe you decided that this was the acid and this was the base. What could you form?
SO3 2 minus.
And?
NH4 plus.
Yep. So this could act as the acid, this as the base. And either answer would be fine. Okay? Because some substances, and we've mentioned ammonia, water, and now you're seeing the hydrogen sulfide ion, have the ability to either donate or accept. They have to have an H to donate, and they have to have a position to accommodate another proton. Question in the back.
No.
Okay?
So like polyatomic ions that are SO, like that are O3 2 minus with the element in front, are they pro?
If it has H something, O something, it's probably both. Although it doesn't have to have an O actually. Hydrosulfuric acid would be another one. It's not as common, but it just came to me. So the point you were making is yes, when you have something like this, something like that, something like this, even like this. But the one I was thinking of was this. This would be another one. Not that common, but you could have it.
Alright, so those all could be.
Yeah,
acids,
they could
bases.
be. There's a whole bunch of them. But water and ammonia are the most common. Okay? So that's your Bronsted-Lowry acid-base definition. And it is a little tricky. Be careful with it. You'll get some practice on it. I think the tricky thing for you is that we're starting before we've finished out on the other one. So just don't let it slide over the weekend. You want to make sure that when you come back, you have a comfort level with acids and bases so that it's not completely lost. But you're good at that, so I don't foresee a problem. Another definition of acids and bases is the Lewis acid-base definition. You will not be assessed on this. I just want to mention it here. And it is an important definition, and it's something you probably saw when you took freshman bio last year. So another definition focuses not on protons being donated, accepted, or generated, but it focuses on whether electron pairs are accepted or donated. Because some acids don't have protons to donate or accept. And so this is going to focus on electron transfer. And in bio, you learned about the electron transport chain, and you may or may not remember that oxygen is the final electron acceptor in the electron transport chain. Sound familiar? All right, those of you who take AP Bio next year or the year after, you'll see it again. And that's an example of a Lewis acid. So a Lewis acid is an electron pair acceptor. A base is an electron pair donor. So the base donates an electron pair, the acid accepts. In order to donate an electron pair, the substance must have at least one lone pair of electrons on its central atom. Otherwise, it has nothing to donate. So what we're looking at, for example, here, and this is a good review of drawing compounds, and I think it's actually a shame that your semester exam is a semester exam rather than a year-long exam, because when you actually put everything together, it just makes so much more sense. But boron trifluoride, hopefully you recall that boron has an incomplete octet, and it will react with ammonia and this substance has a lone pair of electrons on its central atom, so it's going to donate it. This is the Lewis base.
So we don't need to know that?
No.
There's a test?
This is the Lewis acid, and so it donates it, and you get,
Wouldn't the Lewis base have an incomplete
say it again,
Wouldn't the Lewis base not have an incomplete octet?
here.
Yeah.
Here's your octet, 2, 4, 6, 8. This has the incomplete
But it
octet,
just
2, 4,
donated
6.
that.
Well, it shares it. It shares it.
Okay.
And so the Lewis base is the electron pair donor. And that's what you're seeing there. For the examples that are shown, your anions here have gained electrons. This has no place to accept an electron pair, so this is the Lewis base. Same thing with Br minus, which is also shown as an example. And then I gave you sodium ion, which you've lost that electron there, and so essentially this substance has no choice but to act as the Lewis acid. But you're not going to be assessed on Lewis acids and bases. You want to know Bronsted-Lowry acids and bases. They form conjugate base pairs, and you want to know the Arrhenius acids and bases. So take a minute. This is listed as a do now, but this will be a good opportunity for you to make sure you understand the Bronsted-Lowry acids and bases. put the answers up on this screen. If you're not quite ready, just take a minute. There's more than one answer for the first one.
Dr. Kalish,
Yep.
on a test, would we have to recognize that it goes both ways and put both of them? Or
No.
just put one?
I'll just ask for one. All right, the last thing we want to do is just talk about some basic properties of acids and bases. This will be very simple, quick little video to watch, and then I'll give you time to finish up your lab and your quizzes and get you ready for your test tomorrow. So with acids and bases, there are some basic properties of both, and they can help you differentiate the two. When we first started talking this morning, we mentioned eating certain foods, and you of course would never taste chemicals in the laboratory because that could be extremely dangerous. But if you have an apple as a snack, tends to be sour. Lemons are sour, and kids should not suck on lemons. They're so acidic, it messes up the enamel in their teeth. So make sure you don't see little kids doing that. If you're babysitting, that's not good for them.
Wait, apple is good for you though?
Apples are very good for you. All food. No, I said lemons. I said, well, no, it's one thing, okay. It's one thing to squeeze a little lemon in your iced tea, or, you know, sometimes when I make pasta, I'll put lemon on it, a little bit of lemon juice. Lemonade's good for you. I'm talking about kids sucking on lemons at restaurants because they're bored. That's bad. And then also with the acidity, this is a very good point as well. With certain eating disorders, what some kids will do is they will excessively vomit 2, 3, 6 times a day because, with bulimia. And what happens is they'll know pretty quickly if a kid is bulimic as opposed to a different type of eating disorder, because when they vomit excessively, you have hydrochloric acid in your stomach. It's about 0.1 molar, so it's very dilute. It's not like the 12 molar we used the other day. And you'll be doing a titration. You can titrate with hydrochloric acid as well. You could use like 0.1 or 1 molar. I think we're going to use sulfuric. I like it better. But you have hydrochloric acid in your stomach. And when people excessively vomit, they kick that acid that's in their stomach up through their esophagus and then into their mouth and wherever it is that they puke. And that acid eats away at the back of your teeth. And so a dentist will say right away, oh, there's an issue here, very quietly to a parent. And it's something to watch for. When I was growing up, we didn't have any of this. And now it's so prevalent, it's frightening. All right? So acids taste sour, and they can have a very negative effect on your tooth enamel. Bases tend to taste bitter. These are your leafy greens, or if you're washing your face in the morning, you get a little soap in your mouth, you're like, it's yucky. It's a bitter taste. So they taste differently. They feel differently. Dilute acids feel like water. You wouldn't know it. Very strong acids, as we were talking about previously, can burn a hole right through your skin. Please put the phone away. The text isn't important. Bases tend to feel slippery. So that's why they're such good cleaning agents. So when you clean, if you don't wear gloves, feel your fingers afterwards. They're going to be slick. It's also why sodium hydroxide, which is highly basic, if you put it down a drain pipe, all the stuff will slide through. It's also highly exothermic when it reacts with water, so it'll heat it up.
So like nothing's really useful?
There are lots of things that are neutral.
Like I thought water was neutral.
Water is pretty neutral at room temperature. Actually, yeah, room temperature, it's neutral, but as you increase the temperature, it's not as neutral as it was. We can get into that.
What's the stuff they put in like Drano to like dissolve?
Lye, that's sodium hydroxide. It's called LYE, it's sodium hydroxide.
Wait, if an acid will alter your skin, what will a base?
A very concentrated base would also cause a burn, but bases usually are not that concentrated, so we don't worry about it so much. And incidentally, if you spill acid on you, you don't just stick it under the faucet because the burn will get worse because you'll have a highly exothermic reaction. The heat will really sting you. So if you spilled acid on you, we put a little bit of baking powder on you because that has a slight basic nature, and that'll neutralize the acid that you spilled. And we'll go through that when we do the lab because I always have some base out just in case you spill. But the lab is dilute. The last lab was dangerous, but we're responsible and we did a good job. This lab's a piece of cake.
So like anytime you like, how do you know what to do like to neutralize at home?
Well-
you run your stuff at home with like things.
Right. Well, acids neutralize bases and bases neutralize acids, but you don't want to adjust the pH markedly, so you'll use something that has that's basic but closer to 7, and we'll talk about that in great detail next time when we do pH. So let's save that question. I'll make a note to self. Let's see. I have all these notes to self. Where should I stick it? All right, here. So we'll talk about bases or acids that you might want to have on hand at home if you have a spill. Sound good? All right, remind me. All right. Theo, we did react. They react with metals differently. You've seen a reaction of hydrochloric acid with metals. For example, magnesium with hydrochloric acid generates magnesium chloride and hydrogen gas. The lab we did in the first 9 weeks was zinc plus hydrochloric acid. This is a single replacement reaction. This will be on your semester exam, where magnesium is of higher activity than hydrogen. It bumps it out, and magnesium ion hooks up with chloride ion to generate magnesium chloride. Now, for the reaction to occur, this substance must be of higher activity than hydrogen according to the activity series. Bases generally don't react with active metals, so you can see the reactivity of acids and bases do tend to be different with metals. Both substances will conduct electricity. What's interesting is you can examine how strong, not concentrated, how strong or weak an acid is based on its ability to conduct electricity. So you can't figure out if the substance is an acid or a base, but you can determine the strength. Strong acids and bases conduct electricity extremely well, far better than weak acids and bases. There are 8 strong acids that you will need to commit to memory. 3 of them are binary, hydrochloric, hydriodic, hydrobromic, and 5 of them are ternary, and we'll talk more about ternary acids when we name them: sulfuric, nitric, periodic, perchloric, and chloric acid. A strong acid means that the substance ionizes completely, as we stated in the lab the other day. Go ahead.
Memorize these for this year?
Yeah, these you need. So, for example, if you have a strong acid, such as hydrochloric acid, this is what we used in the lab the other day, it will ionize completely. Acids generate proton ions. It ionizes completely, shown by only the forward arrow. If you have a weak acid, this is an equilibrium reaction, like we talked about in the equilibrium chapter. Equilibrium actually lies far to the left, and you get proton and the bicarbonate ion. And this is a weak acid. So the strong acid conducts electricity well because the substance ionizes completely. The weak acid conducts electricity, but not as well because equilibrium lies far to the left. So what you'll see next time is these two concentrations are equal. These two concentrations are not equal. And we'll focus only on the strong pieces. I'll show you this at the molecular level with a little video. Same thing here. If you have a strong base, all your group 1 bases are strong. For example, sodium hydroxide ionizes completely. So these two concentrations are equal, complete ionization, the forward arrow only. Whereas a weak base is an equilibrium reaction. Now if ammonia is a base, does it accept or donate a proton? It accepts, right? So here's the proton. And we'll get into that more. We can take a look at this at the molecular level though. The strong bases include the group 1 hydroxide, so sodium hydroxide, lithium hydroxide, potassium hydroxide, etc. And 3 group 2, calcium, barium, and strontium hydroxide. Those are in your notes. We'll hit that more next time. And then I'll show you the video in just a sec. We'll also be talking about indicators, and we'll talk more about this in the lab. But an indicator is a substance that's one color in an acid and a different color in a base. In middle school, you may have used litmus paper. It was red or blue. And if you dripped acid on it, it's red. And if you drip base on it, it's blue. Did you do anything like that in middle school? Yes, yes? Phenolphthalein is an indicator that we'll use in the lab next week. What you'll see with phenolphthalein is you wouldn't know it was in there in acid, and in a base it's pink. So this is what they use on CSI when they're like looking for blood. They take a Q-tip, they go like this, they go, oh, let's check it for blood. Well, they put a little base on the Q-tip and then they hit it with a shot of phenolphthalein and it turns pink. It's not really great science. Very simple. I'll illustrate that for you next time. pH paper is another type of indicator you can use to determine the pH of a substance. But we'll focus on phenolphthalein when we do that lab. I'll show you the little video now. It just shows you at the molecular level what's occurring and the difference between a strong acid and a strong base.
The strength of an acid refers to the extent that it dissociates into ions when dissolved in water. Strong acids dissociate nearly completely. Weak acids dissociate very slightly. Dissociation into ions means that when an acid, HA, dissolves in water, it transfers a proton to one of the water's lone electron pairs, and the acid anion, A-, and a hydronium ion, H3O+, form. The color change of the water oxygen will make it easier to follow in solution later. The key difference between strong and weak acid dissociation is the final concentration of hydronium ion in solution. Since proton transfer from a strong acid to water is nearly complete, the hydronium ion concentration is essentially the same as the original acid concentration. In contrast, proton transfer from a weak acid to water becomes balanced by proton transfer from hydronium ion to A-. So the final hydronium ion concentration is much less than the original acid concentration. Let's view acid dissociation at the molecular level and focus first on strong acids. The concentrated acid in the beaker consists primarily of acid molecules. As soon as they make contact with the water in the flask, proton transfer from HA to H2O occurs for virtually every acid molecule. Note the change from blue to red. Therefore, a strong acid solution consists of hydronium and A- ions in water and virtually no HA. It follows that the acid dissociation constant
That you
weak acid. As before, the moment the acid molecules make contact with the water, proton transfer from HA to H2O occurs. But in a very short time, proton transfer from hydronium ion to A- balances it and equilibrium is reached. Thus, a weak acid solution has a relatively high concentration of HA.
And so you can see the difference quite clearly there between complete ionization and just partial ionization. Your take-homes today, the different definitions of acids and bases, the difference between strong acids and weak acids, strong bases, weak bases. We'll hit that a lot more next time. And being able to predict products of Bronsted-Lowry reactions.